Hello to those watching online. I've already said hello to people who are here live and in the Zoom live. It's a data analytics revision seminar in semester 1, 2021. And we're talking about, well, we'll see what we can get through. But I've been asked to talk about estimation and hypothesis testing and probability as well, and I'll see what I can do. Okay. You can do it. Okay. All right. Well, let me just say some things. So the big idea in this entire course, it is ultimately about probability really in lots of different ways. And probability, I probably might not necessarily talk about all the details of probability now, but I need to mention some things now. Probability is about comparing what you're thinking of, one specific situation, to all the things that could have happened, or all the things that could happen. So what did happen or what might happen. That could or could have happened. That's what it is. So when you roll a die and you say, what's the probability of 1? You're comparing the 1 to all the other things that could have happened, which is 1, 2, 3, 4, 5, 6. And because you know there's 6 things that could have happened and they all happen the same amount of times, you know that the probability of 1 is 1 in 6, 1/6. That's the basic idea of probability. But the short version of it is that no matter what situation you're in, if you want a probability, then you have to figure out all the things that could have happened so that you can compare what did happen to what could have happened, or what you're thinking about might happen to all the things that could happen. And that's what you have to do. And statisticians and various other scientists of various types have spent a couple of 100 years trying to figure out how probability works, and they're still working on some of the details. And it turns out that some situations produce numbers in patterns that are so common that they've been given names for how the probabilities are described. Okay, so that's the beginning of that. When you have something that has several different options and you want a description of all the things that could happen and how likely they all are compared to each other, that's called a distribution. And the word distribution in English means, you know, the spread outness. You talk about the distribution of a newspaper, which is where the newspaper goes, or the distribution of koalas, which is where the koalas live. And the distribution in probability is where the probability is. It's how the probability is spread out. So that's what it's called. And so every time you calculate probabilities, you are technically thinking about the distribution. You're thinking about all the things that could happen and how likely they all are. Okay. So I probably won't talk about the details of the probability stuff here right now, but I will, if I have time, I will come back to it. Yep. Yep.
I was doing the practice exam online. It says an experiment
Yep.
This experiment has 8 possible outcomes.
Yep.
True or false.
Okay. Do you know what? I'm just going to talk about that for a moment. Let's do that example and talk about how it works. Yes, I have started the recording. Okay. And I'll email you all when it's done, which will be sometime tomorrow. Okay, so let's just do a quick example of doing probabilities. So you're saying a fair coin is tossed 3 times.
Tossing is 3 fair coins.
Oh, same idea. 3 fair coins are tossed, right? Okay. So you have to know what situation the probability belongs to and the ways of recording information about it. And so I've got these 3 coins. That's the object that is having information recorded about it. And each coin has 2 options for how it could come up. So this one could come up heads or tails. This one could come up heads or tails. This one could come up heads or tails. And so I could write down any number of things about this situation. I could write down how many heads there are. I could write down how many tails there are. I could write down what the first coin had. I could write down the information of whether all 3 coins were the same or not. There's all sorts of things I could write down, and all of those would count as like variables. So if I want to cover every possible thing I could possibly talk about, I know that the first coin could be heads or tails. And the second coin, if this one's heads, it could also be heads or tails. And if the first coin's tails, this one could be heads or tails. And then this one could be heads or tails in any of these situations. So we could have head, head. Damn, I should have given myself more space. We could have a head, head, could go with the last one being heads or tails. We could have head, head, which could go tail, damn it, tail, head, which would go with the last one being heads or tails. And we could have tail, tail, which would go with the last one being heads or tails. And so that is indeed, have I missed some? I totally have, haven't I? Let me be systematic about it. Heads, 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 tails, heads. That's all the ones that start with heads, 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 tails, heads, heads, tails, tails. And then heads, that's all the ones that start with heads, isn't it? So now we've got tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Yes, that is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I've covered them all. Yeah, it's true. Now, I don't necessarily have to write down all the options in order to know that there's 8, because there's 2 options for the first ones, for the first coin. And then there's the second coin has 2 options, which could go with any of those 2. And then the third coin has 2 options, which could go with any of those options that have gone before. So since anything can go with anything else, we times them together to get the total. So 2 times 2 times 2 is 8. And I normally imagine this as a great big tree diagram. Have you seen tree diagrams before? So I normally go the first coin. So the tree diagrams are a description of all the possible stories that could have happened. So I could have heads or tails for the first coin, and the second coin, after this is heads, this could be heads or tails, and this could be heads or tails after you've chosen the tails for the first one. And the third coin, this could be heads or tails, this could be heads or tails, this could be heads or tails, this could be heads or tails. And that's called a tree diagram. And because there's 2 options here, and then each of those have 2, now there's 4, and then each of those have 2, so we times by 2 again, now there's 8. Does that answer the question fully? Yeah. And so the probability of any particular thing that I could imagine, in this case, all 8 of these possibilities are equally likely. Because these were equally likely, and then within that, these were equally likely. And so if I want the probability of all heads, then this would be Well, let's just see. How many of them are all heads? There's only one of them that's all heads out of all of the options. And so that's 1 out of the 8 options. You got to be really careful when you do this that everything actually does happen equally now and not often, otherwise it's not going to work that way. And if I wanted the probability of all heads given that there's 2 heads, have you done conditional probabilities like this? So when I say given, that means that I'm now imagining that the whole world only consists of ones where there's 2 heads. So the ones where there's 2 heads is these ones, that one, and sorry, at least 2 heads, sorry. If there's exactly 2 heads, then the probability of getting all heads is 0, because all heads is 3. So that one's got 2, that one's got 2, that one's got 2 heads, and that's it. Have I found them all? Oh, that one's got 3. That one's got at least 2 heads. Head, tail, heads, that one. 2 heads, and then it doesn't matter what happens after that. Heads, we need another heads. Tails, we need 2 heads. No, that's all of them. There's 4 of them. And so that would mean that that's 1 out of the 4 options for what this is. So there's only 4 that are in the story. But you could have done it this way. So I could have said that this is the probability of all heads along with at least 2 heads divided by the probability of at least 2. That's the other way I could have done it, because that's one of the formulas for how to do conditional probability. This we can do as a division. How do you feel about that? Not so sure? Okay, I'll talk about that in a second. So it might be easier to draw it like this. Conditional probability is about pretending that the whole universe is just a smaller piece. So these are all of them. And out of those 8 possibilities, I can do, you know, if I wanted how many have at least 2 heads, I can go, well, there's 4 of those out of the 8. That's half of them. And so these are my at least 2 heads here. They're my at least 2 heads on that side. That way. And so if I wanted to know the probability of all heads out of at least 2 heads, I'm just looking at this bit. And there's only 4 options there, so it's 1 out of the 4. But I can also think of it separately to say, well, just a second, if I thought of this as probabilities rather than individual 1, 2, 3, 4, 5, 6, 7, 8, I could say that the probability of at least 2 heads is a half, because half of them are at least 2 heads. And out of that half, 1 out of the total 8 is 1 out of 8. So instead of thinking of these as individual blobs, I can think of them as fractions of the whole. And so if I want to know what the probability of 3 heads given at least 2, then I could say, well, you know, 1/8 of the time it's 3 heads, but that's only out of half the time. And that's the probability calculation that I was doing here. This "and" here is saying that you only want to include the things that go with this. So in this case, 3 heads is contained in at least 2 heads, and so it doesn't really matter. But if I had at most 1 tail, no, that's the same thing. If I wanted 3 heads out of at most 2 tails, I'm going to have to draw the diagram again. Yeah, nope. Damn it, it's not going to work. Just a second, I don't know if I can do it with this so that they don't overlap the way I want. All right, just a second. So when I do this diagram, this is the bit that I was out of, and this is the bit that I wanted here. And the bit that I wanted was inside the bit it was out of. But sometimes it can go, and it's not going to be able to do it with the heads thing because I can't conceptualize it. Sometimes it goes, give me a second. Yep, here we go. I shouldn't have crossed that out, sorry. Probably at least 1 head, given at most 1 tail. And so when I look at most 1 tail, that's everything I'm looking at. At most 1 tail is, no, I'm going to say at least 1 tail, sorry. Given at least, probably at least 1 head, given you've got at least 1 tail. So these are the ones with at least 1 tail. Those ones. So that's what it's going to be out of 7. And probably at least 1 head is these ones. Right? So at least 1 head is all these orange ones, and at least 1 tail is all these blue ones. But I only care about the ones that have at least 1 tail, so this one doesn't count. And so it's going to be, I can see it, it's 6 out of 7. But I could have done it as that. So the probability of at least 1 tail is this blue bit out of the total. That's 7 out of 8. That's the at least 1 tail. At least 1 head and at least 1 tail, that's this bit where they overlap. Because I don't care about the bit that isn't included in the blue. And so that's 6 out of 8. And so I get 6 out of 7. Because I can times the top and bottom by 8 and it makes the 8s go away. That's the general idea. It can be a little harder in some other situations where it's not so easy to draw the diagram. How are you feeling about that?
That was just a question that I tried to
Let's do it.
is this a PhD graduate have applied for 2 jobs for a job with 2 universities, so uni A and uni B? The graduate feels like she has a 60% chance of receiving an offer from University A and a 30% chance of receiving an offer from University B. If she receives an offer from University B, she believes that she has an 80% chance of receiving an offer from University A.
Just a second. Have I got it? Was it 30% for uni B?
Yeah.
And so say if get uni B, yep.
She believes she has an 80% chance of receiving an offer from University A. What is the probability that both universities will make her an offer?
Okay, I just want to make sure I got the story right. PhD graduate applies for uni A and uni B. Uni A, she thinks she has a 60% chance. Uni B, she thinks she has a 30% chance. But if she does get Uni B, she thinks, that means I've got an 80% chance of Uni A because, everyone wants me now. That's the idea. And so what's probably they both make an offer. Okay, so I interpreted the grammar of what you said to be written this way. Okay. So, I mean, traditionally you would give letters to the events. You would say like, let A be the event that she gets an offer from Uni A, and that sort of thing. That's how they normally do it. Hello? Not again. Revision seminar here, and we're doing some probability problems at the moment. Okay, so let A be the event that Uni A gives an offer and let B be the event that Uni B gives an offer. What we want is the probability of A and B. That's the probability notation version of it. Is that okay? Cool. And we've been told that the probability of just A is 60%, and the probability of just B is 30%. And the probability of if Uni B gives an offer, then the probability of Uni A is 80%. That's what it said, wasn't it? If Uni B, then this chance for Uni A. Okay, so the probability of A is 80%, so the A has to be next to the word to the P, and then the B is and it says if, so that means given B. Okay, so that's how the probability notation works. In terms of the, I want to draw a picture of what's going on here. So I know how to draw pictures of probability information. So these are all the possible situations. And in some of them, A gives an offer, and some of them B gives an offer, and some of them both, some of them neither, one or the other. So I'm going to make, all of these are going to be the A's here. I'll put them on the left. And these are the not A's here. And then I'll put the B's at the bottom. These are all the B's here. That's my little drawing. I could color code them, but can't be bothered. And so this is going to be A up here. So this is B. This is not, damn it. This is not B at the top, and this is B at the bottom, and this is A this way, and this is not A this way. It doesn't really matter which way the arrows point, as long as you've got the thing here. And so this bit here, that bit is A and B. How does your lecture write not? Is it bar or C or what? Okay. Like, yeah, that's what I mean, the complement. Like so A with a little C at the top. Okay, cool. So this would be like AC, right? So the bit that's not A. Okay, cool. Right. So what you've been asked is what the probability of A and B is. We want to know what this is. We know that this bit is 60%. And this bit's 30%. So my diagram's not particularly good. I probably should have made this a little lower to make it look like 30%. If they're independent, then this would have been 30% of the 60%. But I'm pretty sure they're not. And I also know that A and B, A given B, is what this bit this is where B is. This is A out of the bit that's B. So this bit compared to that, that's 80%. So this is 80% of that. It doesn't look like it, but it is in the drawing. So I know that the probability of A and B, that bit, is 80% of the probability of B. That's what that says. But just to be absolutely clear that how the formulas go, the formulas go that the probability of A and B would be, I can think of it as a story. First, I choose that I'm in B, and that would happen that often. And then I would choose out of the B's, I would choose that I'm in A, and that would happen that often. And that probability would come out as probably A and B. And I know what these things are. This is 30%, so 0.3. And this bit is 80%. And so this should be whatever this is, which is, I believe, 0.24. Is that the right answer?
I couldn't figure it out.
Okay. Is that one of the options?
Yeah.
Okay, good. At least it's one of the options. So you know that A and B, there's a few things that you can do. You know that A and B has to be less than the probability of B because it's contained in B. You have to have B and A, so it's got to be less than 30%. So if any of the options are more than 30%, you know it's definitely wrong. And it doesn't really necessarily have anything to do with this, but this is saying what percentage of B is also A. That's what this 80% says. And so it should be 80% of the 30%. I'm just going to draw one more diagram because some people find this diagram helpful instead. This diagram is the tree diagram, which is the story. So we're imagining a story where she finds out that she's got a B first, and that happens 30% of the time. And presumably this is 70%. And then after that, she finds out whether she has A or not. And this says that after you found out what B is happening, this is what A does, and that's 80% there. And then we could also have this situation. So to get both B and A, both of these things have to happen one after the other. And so we multiply the probabilities on the branches and it produces the answer. So those two branches multiply together to give the answer. The Venn diagram makes sense to me in terms of the sizes of things, but this is also another way of imagining the story. So any probability situation that has two events, you can draw one Venn diagram and two different tree diagrams, and one of them will be helpful usually if you're a diagram sort of person.
How do you know the probability when to time something or when to add something?
So that's a very good question. How do you know when to times when to add? Timesing is about, if you've got a story where events happen one after the other, that usually means timing. Or if the Venn diagram, one event happens within the other one. So this one's a certain, and it's usually about conditional probabilities when you multiply them. Yeah, so one happens after the other or one happens within the other. It's the same sort of idea. Addition is about having two separate pieces that are joining together and are about totally different things. So if I wanted, no, it's not independent. Independent, it's mutually exclusive. Independent events have to be able to happen at the same time. So independent, it sounds different to that, but if the information about whether one happens or the other is independent, so since A happening doesn't affect whether B happens, they have to be able to happen together, because if one of them stops the other happening, then they affect each other. And that's a whole language thing I have to talk out every time. So if you can cut your situation into several pieces that are mutually exclusive, then you can add those probabilities together. So if I had, and it usually comes about when the only way to describe them is this or this. So if the only way to describe your situation is thing or other thing, and that word or usually is an indication you're going to have to add. Whereas an and usually indicates a multiplication somewhere along the way, because they have to, yeah. So and is usually times and or is usually plus, but don't bet on it, but it's a good indication. Yeah. So we ended up talking about probability after all.
Quick question.
Uh-huh.
The expected value EX of a uniform random variable X defined over the interval AB, is it A plus B over 2?
Can I figure that question out just a second? Before I talk about that, I just want to check a few details. I'm just going to say a couple of things and then answer your question if that's okay, since we're talking about it anyway. So that was raw probability, just about situations. But you know how back here when I talked about the coins, I talked about some of the things that you could write down about the 3 coins were numbers. I could write down the number of heads or the number of tails. When you write down a number about a situation, it's called a random variable. Technically, anything you write down is random and it's technically called a variable as well, but when statisticians talk about it, they really only care about numbers. And so that means that the things that could happen are all numbers, and you're interested in what numbers are possible and how likely they are compared to each other. And there are different situations that have a tendency to produce certain distributions that always turn out the same. You're rolling a die or spinning a roulette wheel or any of those sorts of things, all the options have the same chance of appearing, and that's called a uniform distribution. But that's a discrete uniform. So it's a number, but there's lots of options, and they all have a probability compared to each other. And the description of what the options are and their probabilities, that's called a distribution, which I talked about already. And some distributions have names. And there are 2 different kinds of numbers. There are discrete numbers, which can only have certain values, usually whole numbers. And they usually come about from counting stuff. And then there's continuous numbers, which normally come about from measuring things. And the reason these matter so much is that the way you represent the probability on a diagram is slightly different. So with a discrete distribution, each number has a probability of its own. Something like that. But for a continuous distribution, there's infinitely many possibilities, and each of them, there's a height on this diagram, but it's the areas that represent the probabilities. So in this one, the height represents a probability. And this one, the area represents a probability. So numbers that have a higher height here are more likely than the other numbers. But if there's infinitely many possibilities, then each of them, like the probability of getting exactly 1.03579214976 is extremely small. And so we're only interested in zones of domains of things. Okay, cool. So the expected value of a random variable is the mean. Like it's the average thing that you would expect to happen on average. And so for a distribution like either of these, it will be here in the middle because these are symmetrical. So the same amount of probability on either side, it'll be right there in the middle, and that'll also be the median. So if you've got a discrete random variable, could you say the words?
Expected value of a uniform random variable x defined over interval a.
So uniform, right? I reckon it's continuous because it's on an interval. And so it was uniform random variable x defined on interval AB. Yep. Okay. So when I imagine what that looks like, the options for what x could be are any number from A to B. So here's A and here's B. And any one of those options is exactly the same chance of happening. And so the diagram will look something like this. They will have the same probability. Well, it's a continuous distribution. You can't really talk about the probability of a single number, like the same likelihood. So the total has to be 1. And so if it's b minus a wide, it has to be 1 over b minus a high in order for that total area to be 1 because it's a rectangle. So, not that that's relevant for this question, I just wanted to point it out. So any probability here is an area. And so if I wanted the probability of being between here and here, I would find that area and do that area out of this area, and that would be the actual probability. But since these are all the same height, it could be this length out of this length, and that would be the same answer. And so that'd be fine too. This is perfectly symmetrical. It's just as easy, if I go to the middle and go, well, it's just as likely to be this way as it is this way, that's where the mean is going to be. Right in the middle, the expected value of x, because it's symmetrical. Things that are skewed, not so much, but uniform distributions are designed to be symmetrical. And the number that's exactly halfway between a and b is their average, so it would be a plus b divided by 2. Yep. So what that wording means is they've said we've got a uniform random variable defined in the interval AB, that's this picture. What's the expected value? It's the center.
So expected value just is the mean?
Yep. But it's the theoretical mean of all the possible things that could possibly happen. So as opposed to the sample mean, which is, add them up, divide by how many there are. There's infinitely many possibilities here. And when I think about all the things that could possibly happen, what's the average of those? And the answer is the thing in the middle, which is the mean. So it's useful to talk about it as the mean, but in a technical sense, can you really do a mean of infinitely many things? Not really, philosophically. And so they came up with a new name for it. But most of us just call it the mean. Yeah. So there are other random variables as well. The other main continuous variable, the continuous random variable you've been told is the normal distribution. And it will be looking like this. And this will be mu, and then this distance here is sigma. That's the traditional. And they normally call it n and then brackets with the mean and the standard deviation, I think.
Oh, yeah, 0, 1.
Yeah, do you say sigma squared or just sigma? That's another difference between different courses in different places. So this is just any normal distribution is this, but there's one very special normal distribution where this is 1 and this is 0 and this is 1. And that is called the standard normal distribution. And it's traditionally called Z. And you normally write a thing like Z is distributed according to a normal distribution with mean 0 and standard deviation 1. And this is really bad. I normally think about it as, oh, look, when you turn a Z this way, it's an N. So that's why I use a Z for the normal distribution. Maybe not.
So the Z-score helps you find the probability?
Yeah, the Z-score helps you find how far away your thing is from the mean in terms of standard deviations. So if you had something that was like this, my normal distributions are getting worse and worse. If you had something that was like this, which was like 10 here and this distance was 2, then if I had this is my x, if x was equal to say 13, then that would be about here. And I could go, well, how many standard deviations, how far is it from the mean? It's 3 away from the mean. And how many standard deviations is that worth? It's worth 1.5 standard deviations. And so we can say that this is the Z-score is how far is it from the mean? And I want to know how many standard deviations that's worth, so I need to know how many 2's fit into it, which is what division is for. And so this becomes, which is 1.5. So this counts as 1.5 standard deviations from the mean. And so what that means is what I've actually done is I've converted my x to a z, and so the same story could be told about this. So with my x, it's just as likely to be 13 or near 13 as it is for a z to be near 1.5.
So once you've converted it to Z, that is no longer
Yeah.
And then use the value from the table.
Yep. Yep. So let me just do that live. So if I wanted to know what's the probability that x is more than 13, that's this bit here, because this is where x is more than 13, and the area that goes with that is this bit here, and that's the probability. And when I convert, that's the same as the probability, and I do the z-score, and that's the same as the probability that z is more than 1.5. And that's this thing here. And then you go and find a table that told you about the z distribution and look up that probability. I mean, really, in the real world, you would ask a machine like Excel what that probability was, because you could say norm.dist, and you could ask it. But economists just really love those tables, and I've never figured out why. Those tables were created before we had computers. We all have computers now. So anyway, so most of the tables, I don't know how your table works. Most tables actually only tell you the left-hand side and not the right-hand side. But they only tell you, yeah, they tell you this area. Some of them tell you this area. I don't know what yours looks like. I can have a quick look. Area to the left of the z-score. So because your table is what we're talking about here. Your table only gives you the left of the z-score. So because your table only gives you this bit, you're going to have to figure out that bit, and you know that the total is 1, so you're going to have to go 1 minus that bit to get the bit that's left over. So I can do that's 1 minus the bit that was less than 1.5. Because the total is 1, and I have to take this bit off to get the bit I want. And the table gives me 1.5, which will be on the second table page. So the way this table works is that I have to go down to 1.5, which is there, and it's 1.50, which is that probability there. But if it was 1.53, I would go over and I'd look at this one here. Yeah. So it's 1 minus 1. Do I really believe that number? I don't like it. I just want to check something. Oh, yeah, okay. I get it. So I was a bit confused because there's like a 99, 8 and 96, 5, and so this will be whatever it is. 1, 8. Something like that. Probably got that wrong. I need a calculator. I don't trust that one.
So if it wants the area to the right, you have to do 1.
Correct.
If it wants the left, you don't have to do the
No, if I wanted this bit, well, it's already in my table, so I don't need to do 1 minus. That's what you're asking?
Yeah.
Can I just look at that table again? Because I have a comment to make about it. Oh, probably. So the Z distribution is perfectly symmetrical. So the area above 1.5 should be the same as the area below minus 1.5. So that's an alternative way of figuring it out.
I'll just do the other side.
Because I could have done, you know, x is greater than 13 is the same as z being greater than 1.5, which is the same as z being less than minus 1.5. Because it's perfectly symmetrical, I can flip the whole thing backwards. And so that is directly in the table. Minus 1.5 is there, 0.06681, which is not the answer I was thinking of. Oh yeah, that's my fault. That's why I needed a calculator. If I put a 1 in this spot, it's going to get like 1.8. So I thought that's totally not going to be a probability. Yeah, and so I could look this one up directly in the table, which is slightly faster. And that could make all the difference in your exam. Normal distribution is the only distribution that's common that does that. Because things like the chi-square distribution aren't symmetrical, so you can't flip them backwards like that, which is sad. Yeah. Good suggestion. I don't know if that's what you meant, but that's how I interpret it, and it's a good one. Okay. Yeah, but other courses have tables that are other than that. And some of them give you, some courses have a table that gives you from the center to the edge, and so you have to add on a half. It's just, wow. That's why I like to check what your table's like. So are they checking in your exam? Are you allowed to use whatever you want? Yeah. So yeah, so you could totally use a machine that just knows how to do normal distributions, and that would be okay. Unless he specifically asked you which row of the table you use, I suppose, but I don't know if he's going to do that. That doesn't sound like a Florian thing to do. For those of you watching this in future years that the lecturer is not called Florian, I apologize. Okay, that's the normal distribution. And I just want to point out that it's still a Venn diagram. It's just that it's a line rather than a blob. So all the possibilities aren't spread out in a circle like the other ones, they're spread out in a line. And so the piece that I want, in the other one, I colored in a part of the blob, but this one I'm coloring in a part of the line, and the probability is the bit. How are we all feeling at the moment about what I've said so far? Okay. Now I want to say, before I move on from continuous distributions, there are many continuous distributions, and they all have, there's lots of them. There's some that you haven't studied in this course. They're called, there's like the exponential distribution and the gamma distribution and all of those. But you have, even though you've technically only been told about the uniform distribution and the normal distribution to do probability calculations with, you actually have, because you've been told about the t distribution and the probably chi-squared distribution. No, okay. You've been told also about the t distribution, which looks like a normal distribution to the untrained eye, but is slightly different. And there's not, in the same way as there's not one normal distribution, there's infinitely many that all have different means and standard deviations. There's a whole list of t distributions, one for each degrees of freedom. Yeah. And what happened back in 1917, I think it was, could be earlier, could be later, roughly there, 19 teens to 20s, is that Gossett, who was working for the Guinness Beer Company, invented the t distribution and the t-test in order to compare the yield of yeast. There you go. And he published his results under the name student because he wasn't allowed to publish under his own name because all his research belonged to Guinness. That's why it's called student's tea. Yeah. Isn't that fun? And Gossett was a very nice man. Someone gave him an award once for being so helpful to statistics, and he said, "Oh, that's okay. Fisher would have figured it out if I hadn't." Fisher invented most of modern statistics. There's an F statistic. Have you done multiple regression? Okay. But have you done it just with one there's an X and a Y, but not two X's? Okay. Right. That's econometrics 2. No. Econometrics 2 is all regression all the time. So just so you know. You can still talk to the Maths Learning Centre about that too. Okay. So you've been told also about the t distribution. And it looks similar to a normal distribution, but it actually gets taller and taller flatter and flatter the higher the number of degrees of freedom. And the degrees of freedom, I just think of it as the distribution finder. It says which distribution is it, and there's a big list of them, and you just got to find the right one. And you'll be doing things similar to this with it as well. What Gossett discovered is that the Z distribution doesn't really work if you don't know the standard deviation, and you have to estimate it yourself, and all your p-values are wrong. And so he discovered the T distribution, which was more accurate, basically. All right, and there's one named discrete distribution that you have been taught, which is the binomial distribution. I promise I will talk about the hypothesis testing as well. So the binomial distribution is a discrete distribution, and it's designed specially for counting how many times something happens in a group. Technically, they call it a fixed number of trials. But I imagine it as, you've got all these people and you know how many people there are to begin with. And you count how many say yes. And since they could all produce all different options for yeses and nos, I mean, there are technically for this, like with my coins, there were 8 options, and this one should have 2 times 2 times 2 times 2 times 2 options. And each option happens a certain number of times. And just like with the coins, it's much more likely to have a mixture of heads and tails than it is to have all heads or all tails. It's the same idea here. And the binomial distribution counts how many yeses there are, and there's an answer for the number of yes. Could be 0, 1, 2, 3, or 5, and each of them has a probability. Whatever it is. And there's a formula for what this probability is. And it all depends on, for each individual person, how likely it is for one person by themselves to say yes or no. And so they often call this P, the probability of yes. Does your lecturer call Q the probability of no? The probability of yes for one person is P, and the probability of no for one person is Q. I mean, it could be the other way. You could be interested in counting no's, and that'd be fine as well. And so then the probability that the number, X is the number of yeses. The probability that the number X is equal to a specific number is the number of individuals, which in our case is 5, choose the number of X. Is this the symbol you've seen, or does he say NCX? Or does he put the factorials in? Good-o. Like that. And that's the formula. And what that means is that if you want, in this situation, so e.g. the probability of one person says yes by themselves says yes, if that probability was, say, 60%, then the probability that 3 out of 5 say yes should be a binomial distribution, because I'm counting how many out of a group, and they all have the same probability and they don't affect each other. Then this would be 5 factorial on 3 factorial 2 factorial. That's what this bit is saying. The n is the 5 is how many people there are. The 3 is how many people I'm saying yes, and this bit is everybody else. And it's going to be the 0.6 to the power of 3. So these are the people saying yes, and this is how likely each person is to say yes, and this is how many of them there are, times the rest of the probability to the power of the rest of the people. Yeah. And this will be whatever it is. Like, could ask a machine to calculate that. I'm not going to do that. But I really want a number, so I'm going to get my calculator to do it. Oh, wow. 0.3456, what a coincidence. That's so cool. Okay. That'd be the coolest thing for me to randomly remember. So, and that probability is 0.3456. Okay. That's so cool. Anyway, sorry about that. Yeah, that's basically it. If you want to know the probability of, 2 or 3 out of 5, you're going to have to figure out 2 and figure out 3 and add them together. Yeah. So how are we feeling about the general idea of distributions before I talk about hypothesis stuff? And that goes for you, whoever's left in the Zoom. I did think of one thing. The expected value of this x is how many people would we expect to say yes on average out of the 5? Well, we expect 60% of the 5 to say yes on average, which is 3. Doesn't always work out to be a whole number, and it's okay for it not to be a whole number. And so in this case, 3 is not just the mean, but it's also the most likely. Yeah. In fact, with a binomial distribution, the most likely number is either the mean or one off from the mean. Yeah, cool. I want to show you something. This is the Desmos graphing calculator. It can do distributions. So I have 5 trials. The success probability was 0.6. And those heights there are the probabilities of each individual number. So the probability of 3 is 0.3 something. That's about right. And I can even ask it what the things are. There we go. So I can say binomial distribution, PDF stands for probability distribution function. So there you go, in case you ever want to use a machine to do it, it can actually do that calculation for you. Cool. And it can draw normal distributions too. There's my normal distribution with mean 10 and standard deviation 2. And I can click this and ask it for the probability between, say, what did I have? I had 12, 13. 13 and infinity, and it draws the picture and tells you the area as well. Cool, huh? Yeah. You probably just need to know that your table rounds off to 4 decimal places so that you can copy the correct answer. It can also do from, say, from 7 to 13, and it will tell you that all by itself. Yeah. If you ever want to check your answer from doing it the long way. Okay. So here's a good question. Why would they spend all this time telling you about probability distributions if the ultimate goal was to do hypothesis tests? And the answer is, well, I'm not 100% sure, but the t distribution turns up, and you are going to have to know the general vibe of calculating probabilities by doing areas, even if the computer's going to do that bit for you. And the idea is still there. The idea that any situation, if you think of all the things that could have happened, that's what probabilities are talking about. And so when you're doing estimation and testing, In both of those situations, you are living in a land where you don't really know what's going on. And that is the real world. You never know what's really going on in the real world. Everyone's just making crap up. And so you might have a general idea of how it works, but you don't know a specific piece of information. And what you have to do is that you're going to collect data, right? And you're going to like calculate something. Say it's a mean. I'll do a mean today. There may be more than one mean. Maybe instead of calculating a mean, you'll calculate a proportion. Like what percentage of people said yes? And then what you want to do is you want to say, well, this is what my data said, and I want to imagine what the world is really like. And so what I'm going to do is I'm going to imagine all the data I could have collected and think about how likely the mean that I got was if I think about all the things that could have happened. And that's exactly what a probability is. Yeah. So there's two ways of thinking about it. One way of thinking, well, and the other thing about probability distributions that's useful is that you're imagining that this collecting data came from some land somewhere here that had a distribution. That the data you collected, there is somewhere a big list of all the things that could have happened, and you collected some of those things. And the description of all the things that could have happened is the distribution. And so the idea of there existing such things as probability distributions is an important idea. But whether you need to spend weeks calculating probabilities under normal distributions in order to get that idea is a whole different story. But that's the big idea. And so there are two things that we can do. We can wonder if the distribution was of a certain kind, then does that mean that I should be surprised by the results of collecting the data? Because if I am surprised, then maybe I don't believe in the distribution that I was thinking of. And the other one is, sure, I could do that, but which ideas for the distribution am I not surprised by the data? So I can think, for example, that maybe my distribution of a measurement of, say, if you recorded some sort of fabulous psychological test on people and you gave them a questionnaire and you added it up, it normally comes from a normal distribution, approximately. And you might think, cool, my psychological test for statistical distress, everyone gets a score of, on average, maybe people get a score of 50 out of 100. Is that the truth? And so I collect some data and I look at the data, and my mean comes out to 40, and I'm going, is that unusual? If it really is 50 on average, is it unusual to get 40 in a group of 10 or not? And if it is unusual to get a group of 10, does that mean that maybe it's not really a mean of 50 after all for all the possible people that could have done it? Or maybe, and which possible means for all possible people would mean that my 40 in my group isn't surprising. That's the general idea. So that's both of those things. So, right, stepping back, the estimation and testing answers two questions. So the estimation answers this question. What is the number? So if you're sitting and your exam question or your own curiosity is saying, I wonder what the average weight of a packet of cereal really is. It says it's 500. What is it really on average for all possible packets of cereal that this factory produces? That's a what's this number question. And so I wonder what percentage of people percentage of kids actually do finish their homework every night. That's a what's this number question. And there are lots of questions like that. I wonder how likely it is for both sides of a bus to have a big poster on it. Like those are what's this number questions, and they're answered with estimation. And we know that you can never say what the correct answer is, because, I mean, unless you looked at all the buses, then you could know. But with your factory that produces cereal, well, the cereals that you're interested in don't even exist yet, because those are the ones that are going to be produced next year. And they don't exist. And if you're a person in medicine, you're wondering about babies, the babies that you're interested in don't exist yet. And so you can't measure all of them because they don't exist. And so you have to guess based on what you've got. And so since you know that it's never going to be the one correct answer, you do a range of possible answers. And that range is called an interval estimate. Or if you like, a confidence interval. So the idea is that if you calculated a mean and the answer was 40, you would be totally not surprised if the mean of the real distribution was 40. If the mean really was 40, then it could totally produce a mean of 40 in your sample. But you also want to know what other numbers would be unsurprising to get a 40, and that's the zone. So you used to have the 40 and you go up a bit and you go down a bit, and these are the ones that are consistent with my data, that if they really were the true mean, for all possible things that could happen, then I would be unsurprised at 40 happening, or whatever number was. That's the idea. And you have to choose a number for your level of surprise, or the opposite, which is your level of confidence. So 95% confidence means that your level of surprise is at 5%. If something only happens 5% of the time or less, then you find it surprising. That's the idea. Okay. So never use the word surprise when you're talking about your exam, that's fine. It's a multiple choice, so you're not going to get a chance, but that's the idea. 5% chance is surprising. And you can do 99% confidence or 90% confidence or whatever. But 95 is the most common because Fisher, when he invented this, did 95 the first time. And everyone just, it's not a bad number. Okay, people like multiples of 5. Testing answers these questions. Yes or no? A test, a hypothesis test, a p-value, can only answer yes or no questions. It's the only kind of question it can possibly answer. And the yes or no questions are of the flavor, usually concern a particular number and what value it has. Or two numbers values, but it's a yes or no question. So the yes or no question could be, is the mean of all the possible cereal packets that this produces 500 grams like it says it is? It could be, is the percentage of children that finish all their homework every night more than 50%? It could be, do men and women have the same chance of participating in volunteer work? It's always a yes or no question. It could be, is there a linear relationship between these two numbers? They're always yes or no questions. So this is the question it's asking, but the way that you do it when you write it down is you always reference the number itself that you're talking about. One of these answers, yes or no, is called the null hypothesis. Whichever of them is the one that's the null hypothesis is the one that talks about, that only has one way to be. I'm going to talk about that. So when you do hypothesis testing, usually it's, is this number equal to this specific option? That's one kind of question you could be asking. Is the mean equal to 500? Is the proportion equal to 50%? That's the sort of thing. And the null hypothesis in that situation is yes, it is equal. And that's because there's only one way to be equal. There's lots of ways to not be equal to a number. There are many, many ways to not be 500. There is only one way to be 500. And so that's how I tell what the null hypothesis is. It's the one way. Are these two numbers equal? And the null hypothesis will be, yes, they're equal. I mean, this is what I'm saying in my head, but I'm actually saying like mu equals, 50 or whatever it is. And this one will be more like mu1 equals mu2 or something like that. And then if it's like, is there a relationship? The null hypothesis will be, no, there is no relationship. And the reason it's no is there's many, many ways to be related. There's only one way to not be related. There's only one way for something to not affect another thing, and that is to not affect it. But there are many ways to affect things. Sorry? This is HO. So that's what I'm saying. It's the null hypothesis because it's the option that only has one way to be. Also, if you really want to talk about it, then you can also say that, well, it goes with the slope. Did I use beta in this? We did regression only a few weeks ago and I've forgotten now. It goes with the slope being equal to 0. And there's only one way to be 0. So that allows you to do it all in terms of numbers being equal to stuff. But I just wanted to point it out because some hypothesis tests that happen later are just in words. And if you're thinking about being a relationship, the answer of no relationship is the one that has one option. Because there's more than one way to have a relationship, but there's only one way to not have a relationship. Yeah. So the null hypothesis is the one that only has one option. Okay. So the reason you have to choose the one that only has one option is because you have to do some maths. And if you don't know what mu is, you can't do any maths using the number mu. But if you think that mu is 50, then you can do some maths using the number 50. That's the reason why you have to pick the one that has only one option. Because if you say, oh, well, it's not equal to 50, so is it 49, 49.5, 40, 51.6? Which number am I going to use in my calculation? That's why. Okay. And, people who talk about this will say, oh, it's about, innocent until proven guilty and blah, blah, blah. It's really just a maths thing. It's not really about philosophy at all. They'll say, oh, no, null means no. It means there's no change. No, it's one option. So just, it does mean no. It generally means no difference. Yeah. Oh yeah, I mean that's all good stuff. It's all good stuff, and it's lovely stories, but it doesn't necessarily help you to actually choose which one you want. So that's the problem with metaphors. I'm over in one of the other courses I teach mathematical induction, and that's a mathematical proof process. And people go, oh, it's like a game of whispers. It's like, sure, but how do I actually do the proof? Like, I get the metaphor. So that's how I feel about hypothesis testing. I get the metaphor. What do I do when I do the calculation? That's where I want to be. Okay, so every situation, yeah, all right, so here we are. I'm going to have to figure out some things. When you do a hypothesis test, your lecturer talked about there being 6 steps. I can't remember the exact steps. You can look them up. But the idea is that I have a question, a yes or no question. That's the beginning. I have a yes or no question in my mind. And what I would like to do is that for the purposes of appeasing people who want to know how the calculation really works, I have to pitch that question as being about a number if I can, or 2 numbers. And then I have to figure out a calculation that I will do on my data. So pitch it. And choose a null hypothesis. That's the first step. And it'll be, you know, mu equals 5, or mu1 equals mu2, or b0 equals 1, or whatever. And you're probably going to have to choose an alternative hypothesis as well. And the alternative hypothesis is about the conclusion that you want to make that isn't about yes or no, but is about the size of this number. I find that really difficult, but it will be embedded in the words. And if you can't figure it out, then just choose it to be not equal, because you've got to pick something. All right. So that's the beginning. And then what we're going to do is we're going to pick a number to calculate. This number is called a test statistic. All right. So I need to pick a number to calculate that will be bigger the further away from the null hypothesis I am. That's what I want. And I also need to pick a number that I will know, well, I'll get to that in a minute. So I have to pick a number to calculate. And while I'm picking that number, I have to imagine all of the data that could have happened and all of the answers for this number that could have happened for all of that data. That's what I have to imagine. Or I have to get Fisher or Gossett or Pearson back in the 1920s to imagine it for me. That's what I want to do, really. Okay, because then they'll do a nice little probability distribution table and I can look it up. But that's what I have to do. So I have to imagine all possible data and all possible numbers that could have happened. And then I want to compare my test statistic to all the others that could have been. Not that it matters me writing it down, but it just makes me feel better. That's what I have to do. So this is called the test statistic, this step. This bit is the distribution of the test statistic. Because that's what a distribution is. It's all the things that could have happened and how likely they all are. And I want to compare my statistic to all the ones that could have been. That's me figuring out the p-value. Or if I like, figuring out a critical value as well. So there's an E in imagine. Now, here's the thing. I'm going to imagine that I'm living in a land where the answer to this question is whatever answer it is. Yes or no, whichever is the null hypothesis. Because I'm thinking, if the answer really is yes, then if the answer is really yes, let me imagine all the possible data and all the possible test statistics that could have happened and compare that to the one that actually happened and decide if I'm surprised. We go, I got a test statistic of 4. Well, okay, under the answer, so the position that the number is like 50, What are all the things that could have happened? Cool. And oh man, 4 is like horrifyingly unlikely. Maybe I don't believe that the answer is yes or no, or whichever the answer is. That's the idea behind it. So here's the thing. This bit here is the hard bit for our statisticians who are inventing hypothesis tests. Because you have to pick a test statistic that you know the distribution of. If you don't know the distribution, you can't do this bit where you compare the test statistic to all the things that could have happened. So you have to pick a calculation that will produce something that you know the distribution of. And hopefully it's one with a name that you can just look up. And this is where all of those things about known means, known standard deviations and unknown standard deviations and pooled standard deviations and all of that is about the statisticians going, what's the best guess I've got for what this distribution really is? So that's hypothesis testing. They don't show you this bit in most courses, but confidence intervals is this, but for every possible answer for what the number could be. So if you do this whole process and go, my first yes or no question is the mean 50? Blah, 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 nah, don't believe it. Is the mean 51? Blah, 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 nope, don't believe it. Is the mean 52? Blah, 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 yes, I believe that. Is the mean 53? Yes, I believe that. Is the mean 54? Yes, I believe that. Is the mean 55? Nope, don't believe that. And so the zone from 53 to 55 is the one I believe. That's the confidence interval. And so that is the long way of calculating a confidence interval. I'll just do a hypothesis test for every possible number and see what I get. But what you can do is you can just do the calculation for the hypothesis test backwards to try and figure out what the original numbers should be to make this come out to be a p-value over 0.05. And that's why the calculations for a confidence interval and a hypothesis test use the same pieces but in a different order. Right, so let me actually do one. So here's my question, is the mean that? So for example, so you might have a null hypothesis. The mean is equal to 50. And your alternative will be less or more or not equal or whichever one it is. I've got a good yes or no question. I've picked a specific answer, and I've picked the null hypothesis to be a one way to be. And then I need to pick a test statistic to calculate. And I have to pick a test statistic that I know the distribution of. And there are different situations which would tell you whether you know the distribution or not. So if I know the real value of sigma, which you never do really, I mean, honestly, nobody really knows the real standard deviation, but we do it anyway, because this is what existed before Gossett invented the t-test, and this is the best they had. Then I can calculate this test statistic. The sample mean minus the 50 divided by the standard deviation on the square root of the sample size. Does that look right? Good. And this, if the mean really is 50, and I imagine all the test statistics that could have happened for all the data I could collect for all of the samples of size n, then this will have a distribution of a standard normal, which is why it's called Z. And so when Pearson and Fisher and friends just did statistics, they went, cool, this I can do. And they knew that it wasn't quite right if they didn't know the standard deviation, but they went, well, this is the best we've got. And so what you do is you look up the actual mean that you did get and you compare it to this, and you draw your little diagram and you go, here's mine and here's the p-value. But you could also go, well, actually, if it's two-sided, the p-value is for both sides. because I'd be just as surprised if it was 55 as if it was 45. Like 5 above the mean would be just as surprising as 5 below. And so I do both sides. So that's that. But if I don't know what sigma is, Gossett discovered that you should do this test statistic. And it's not a Z anymore, but interestingly, he did call it a Z in the first journal article he published about it. You'll do the sample mean minus the normal, just the hypothesis that you're interested in, divided by the sample standard deviation divided by n. Anyway, yeah, if you do this, the actual distribution of all the things that t could have been is a t distribution with n minus 1 degrees of freedom. Is that how your lecturer writes it? Yeah. So Gossett went, hey, there's this big stack of t distributions, and you just have to go up the tower until you find the n minus 1, the one for n minus 1, and then you look there to find your probability. And I think that's it for is the mean equal to a number. I think they're the only two possibilities. Pretty sure. Yeah. Okay. But what if, we've answered the question, is it equal to 50? What if I wanted to know what it really was? Like, is the mean equal to 50? What if my question was, what's the mean? This doesn't have a null hypothesis, but technically it does. Every number is in a different null hypothesis. Is it equal to 50? And I'll get a yes or no answer. Is it equal to 51? I'll get a yes or no answer. Is it equal to 50.5? I'll get a yes or no answer. And so what I'm going to do is I'm going to do this backwards. I'm going to go, see this thing here? That's my mu. I'm going to rearrange my formula to make this the bit that it's equal to. Watch this. You don't have to actually do this, but I just want to show you where it comes from. If I want this mu here, I would have z times sigma en root n. That would get rid of the sigma en root n from my formula. It's divided, I'll multiply both parts. And then I'll add mu to both sides, so it's this. And then I'll subtract this from both sides. Look, confidence interval formula. That's where they come from. The reason why it's a plus or minus is you'd be just as surprised if this was a negative answer as if it was a positive answer. You'd be just as surprised if it was this far above the mean as if it was this far below the mean. And so you want technically a plus or minus along the way. That's right at the beginning. And I'm going to move the plus or minus over here like that. There you go. And what you do is it's usually called Z star. Does your lecturer call it Z star or Z critical or something? Yeah. Because you don't really, this is, the thing is that your decision will be that it's surprising if your Z statistic is further out than the critical value. And the critical value is the one that would have given you exactly 0.05 or whatever it is. And so you only care what we're doing here is we're undoing the hypothesis test to find where the edges are. Which mu's would produce a Z right at the edge if I did the hypothesis test? Right where the crossover between P below 0.05 and P above 0.05 is. That's what I'm doing. So most people are good at good at looking up these formulas. Some people are good at remembering them too. But that's why they use the same pieces, just in a different order, in case you've never thought about that. Yeah. Cool. And so this goes with if you know the standard deviation. And this one, if you don't know the standard deviation, it will be this rearranged. It will be x, the real mean is x bar plus or minus t times s on root n. And we rearrange the same pieces. The t will end up here, the s on root n will end up here, the x bar will end up here. But technically, this is the edges of the mu. It's not all the mu's. The mu's is everything in between here. And then you'll find those two numbers. You'll do the plus, and it'll get one number, and you do the minus, and it'll get another number, and you'll put it in a little thing like that. Yeah. But this is short for from this number to this number. Because you don't want to use a little dash for 2, from 2, because that looks like a minus and we all get confused. So, yeah. Okay. That's the what's the mean. There's 2 situations, and it's based on our statisticians being clear about what the distribution was. What about the what's the, not a what's the, I'm still not sure if we did hypothesis tests for proportions or if we only did confidence intervals for them. I can't remember. There'd be p-hats. They're like, is the proportion equal to this number? And so, you know, for example, H0, the proportion is equal to, say, 0.5 or something. But I won't use 0.5, I'll use 0.6 because it's easier to see what's going on. And so then you'll go, the test statistic is also a Z, and it's p hat minus the 0.6 over the square root of the 0.6 times the 0.4 divided by n. But if you wanted to answer what is a proportion, just so you know, this p hat is your current estimate for what p is. So it's really confusing. The true mean is mu and the sample mean is x bar, and the true standard deviation is sigma and the standard deviation is s. And in this one, the true proportion is p and the sample proportion is p hat. It's not like there's any consistency here. They're all different. Whereas what is the proportion would be the proportion, you know, the edges of the proportion is the p hat plus or minus the 0.6. So plus or minus the z times something in this spot. So the difference is that in this one, it will be the P and the Q from the null hypothesis. This one has a P hat and a Q hat from the sample. Because you already know that the null hypothesis, usually by the time you've done this confidence interval, you already know the null hypothesis is false. And so you're not going to use this number because you've stopped assuming it's true by this point. So the best estimate you've got for what this number really is the number you've got in your sample. Cool bananas. How are you feeling? I'm trying to line them all up next to each other so it's easier to see what's going on. And then there's one more. I know I've gone over time, but I really want to do them all. Are the means equal? That's the question that we're asking. And the null hypothesis usually goes mu1 equals mu2. Because only one way. This is for 2 populations. You can also pitch this one as, does being in a different population make a difference to the number? So usually when you're actually designing research, you're going, oh, does what country you're in make a difference to you? If it's numbers, then it's just crap. Proportions are easier to talk about, to your opinion of blah. But yeah, some people would say, does what year you do this course make a difference to your grade? And that's now saying, is the average grade different in the 2 different semesters, in 2 different years? So if you can pitch it as are the means equal, then it's good. But your original question is often about relationships. Yeah. So that's what I was saying. Like, if there's no relationship, that usually means that something is equal. Yeah. Okay, so the means are equal. Or are they? That's the question. And there's lots of different situations about what would cause you to have different distributions for the things that you calculate. And so when they first, if you happen to know the 2 standard deviations and you think they're the same, then there's one calculation you can do. Right. And that's, I'm going to have to look this one up. Just a second. That really was weak. Damn it. This is the one. Just a second. Lost it now. This one. 2 populations. That's what we're talking about here. I've started with this one. The standard deviations, you happen to know what they are, and they happen to be equal, then you get this calculation. I'm going to write that down. No, I'm not. I'm just, that's what it is. So we have this x1 minus x2 is the difference between the 2 sample means. Mu1 minus mu2 is the difference between the 2 means, and we want to know how different the differences are. And then you divide by this, and this is the pooled standard deviation, which is this. Oh, that's unknown but equal. Okay, known but equal isn't different to known but unequal. Sorry. There's 3.
Yeah.
So, damn it. I'm going to do 4. It doesn't really matter, but I just wanted to. So if you know they're equal, then it's just a t-test again, an ordinary one, because if the standard deviations are equal and the means are equal, it's just one giant group. And so we're going to go that the t is equal to the difference between the 2. And technically, if they're equal, the difference will be 0. Really, right? So we can just put 0 in that spot. And then it's going to be like that. So if they're not equal, then it'll be the same thing, but like that. It won't make any difference. If you know what they are, it'll be the same calculation. And this will be from a t distribution with n minus 2. But these do n1 plus n2 something, doesn't it? Yeah. But yeah, n is the total number of individuals in all the groups together. So the reason that it's that many is because if you know what both of the sample means, because we're comparing this value of t to all the t's that could have happened, and we know what the sample means have worked out to be. So if we imagine all the t's that, all the calculations that could have happened that will definitely produce these same sample means, I can change up to this many of the individual data points before I have to know, what the last, figure out what the last one is to make the mean come out to the right answer. So if I have 3 numbers and I know that the mean is 5, and the first one is 6 and the second one is 7, they currently add up to 13. The only way the mean is going to be 5 is if the last one's 2. And so I can change all but I can change up to 2 of them before knowing what the mean works out to be. The last one has to be whatever it is. And so that's the degrees of freedom idea. All but 2 of the data points can be moved before I end up having to be forced to change the sample means. But I know what the sample means work out, so I'm imagining all the t's that have the same sample means that mine have. That's the idea. I don't know if it's helpful. If it's not, just ignore it. Okay, so that's that. And that's not even a t, that's a z, sorry. I was completely wrong. That's a z. Ignore that completely. That's a z. Sorry. Let me just check. It's a z. When you know the standard deviations, it's always a z. Whether it's 1 sample or 2 samples, it's always a z if you know the standard deviations. Well, as long as your original data came from a normal distribution anyway, like that's technicality. If you don't know, them, then it may be that you can assume they're equal though. And your usual way of testing that they're equal is the usual way of testing whether they're equal is to figure them out, and if one of them isn't bigger than twice the other one, then you can assume they're equal. Did your lecturer give you a way of telling if they're equal? Or did he just say assume they're equal in the question or something? Right, okay. There is a way of telling, like if one of them isn't more than twice the other one, then you're okay. Which is also a hypothesis test actually, because the critical value is 2. Yeah, so that's a hypothesis test as well, which is very interesting. And they teach that in econometrics too as well. So this time it really will be a t, and it will be, I'm going to go not equal first, if that's okay. If they're not equal, it'll look exactly the same as this z. Only these will be sample standard deviations. And so this is the same as the difference between what it was for a single population. We changed all our sigmas to s's, and it's changed my z to a t. I'm just going to check if I'm right about that. Yep. So that's what happens here. And the t distribution is the t distribution with a number of degrees of freedom in this spot, which is complicated. It is that. Because of course it is. That's obvious. That's Welch who did that. He figured out that adjustment for the t. Some people say that you just pick the smallest value from n-1 minus 1 and n2 minus 1 and use that. Or you just trust your computer and it figures it out for you. But yeah, have you been expected to calculate that before? Yeah, but normally if...
More often than not, he's given us questions where they're either equal or you assume they're equal.
Okay.
I reckon
have you used Excel to do this sort of things, or have it all been by hand? Oh, God, what are they doing? Sorry. So you haven't like got data and then asked it to do like a t-test for you and it just spits all out all the answers? You know how we did it with regression? You haven't
done it for the assignments, but that's it.
Right.
Then
Okay.
you just have to do it in class.
Okay. Cool. Just a second. So I'm back. So the other situation is when you don't know the means, don't know the standard deviations, but you do know the, I'm just going to finish this off. It's complicated. Okay. I put these two together, even though this is the most complicated one here, because these are easier to see how they're related to each other. So what, probably Fisher, because Gossett invented the straight up t-test for one sample, and then Fisher did basically everything else. But I have no idea. It's a safe bet to say that Fisher invented it. What they did after this is what they wanted to do, and they knew that it wasn't really a t-distribution. It was pretty close, and if you choose the correct degrees of freedom, it'll come out to the right p-value, and so they did this. But they did this much later. What the original assumption was that the standard deviations are the same, because this was too hard. And so they went, this is too hard. What if the standard deviations are the same? And then so they technically, in order of time, created this third one first. And that's why you get taught it second. So what you do is you say, well, if the standard deviations really are the same, then it's just one giant group, right? The two groups that I thought I had are really just one big group that all have one big standard deviation. So I could just do a giant sample standard deviation from the entire two groups. That's really what we're doing. The pooled standard deviation is pretty much that. But what we do is first we're going to estimate what the standard deviation is. And there's this formula for it, which I shall look up because I can never remember it. Because again, I usually let the computer do this for me. Which is not quite the same as just a big standard deviation from the giant group. Because if it was a big standard deviation from the giant group, it would be n1 plus n2 minus 1. But there's some technical details that make it biased if you don't do it this way. So gloss over that. And then you go that the t statistic is that. Your lecturer puts the SP squared on the inside of the brackets. So I'm just going to draw several versions of this, if you like. So there's this version. This one makes it easier to compare to this one. So they are in fact exactly the same, except that instead of using the individual standard deviations in this spot, we use the pooled standard deviation in both spots. Because the idea is we think the standard deviations are equal, so we're going to figure out one estimate of the overall standard deviation and use it in both positions. That's the difference between them. Yeah. So this one uses sigma 1 and sigma 2. This one uses S1 and S2. This one uses SP and SP. But this simplifies to that because the SP is in both parts and I can factorize it out from the algebra. I've never drawn it that way. I'm so excited. Cool. And this comes from a t distribution with n1 plus n2 minus 2 degrees of freedom. In general, this degrees of freedom will be lower than this degrees of freedom. In general. Could be wrong. Yes, lower. Higher degrees of freedom is better for a statistic. And that's the difference. And the calculations will be the same after that point. You'll look it up in the appropriate distribution and you'll find the p-value and you'll make a decision. And to get the confidence intervals, you can do the same thing and rearrange these pieces into the confidence intervals. So you can, with the confidence intervals, you can have x1 bar minus x2 bar. And this time you don't know what the difference between the two means is. And you'll divide by some square root of crap, right? And then you can rearrange that to, and that was the t, right? They're all this shape. And so that means that the confidence interval, it'll be a t or a z, could be a z. The confidence interval will be the mu1 minus mu2 is equal to x1 bar minus x2 bar plus or minus the t times the square root of whatever that crap was. But it will be a z if this is a z. So I can't remember them separately because they're all got the same bits and pieces. So it's easier to remember just one of them. Yeah. So your lecturer went through all of this stuff first and then did the hypothesis test after. I find it easier to remember in the opposite order just for myself. But they are the same ideas. How are we feeling? There's at least a summary.
Can you go through one specific question?
Sure.
It says two independent random samples of 25.
Oops, stop just a second. Two independent samples, 25 observations each. Yep.
Are drawn from two normal populations.
Yep.
The parameters of these populations are the population 1 of the mean and the standard deviation of 50. For population 2, the mean is 130, standard deviation is 45. And then it says find the probability that the mean of sample 1 will exceed the mean of sample 2. Yeah.
Now, here we go. This is not, so this is a different question, right? This isn't, so those hypothesis tests and confidence intervals are about having a sample and figuring out what's going on with the population means. This is the opposite. I've got the population means and I want to know what's going on in the sample. So this is not at all the same, sadly, but it's okay because the reasoning that produced the calculations we do in the reasoning that produced the calculations we do in this stuff is the same, is similar. So I'm going to have to step back a bit. So this is great. So if we're here, the reason this happened is because we had two populations and they have sample means that are created from those populations. And those sample mean, you know how I said every situation has a distribution? Right, so here's my big distribution for individuals that belong in population 1, right? So this is for one person in population 1, and they have a mean of 150, and they're not necessarily people, but whatever. And the standard deviation is 50, and this is one person in population 2, when they have a mean of 130 and a standard deviation of 45. And so this is telling me how likely it is for one person to have any particular number. They're much more likely to have something close to 150 than 200 and various other things. And then what I do is I think, oh, I've got 25 of these people. $25 people, that's what I'm imagining here. And each person has a number, right? So that this group of people, the combination of all the numbers that they could all possibly have has a distribution of its own. It's a multivariate distribution, which you didn't learn about, but that's a thing. And then I'm going to calculate from these 25 people the sample mean, which I should call x1. So if I imagine all of the possible groups of 25 people that could possibly have happened, and they will each produce a sample mean, and I imagine all the possible sample means that could have happened, these have a distribution of their own. X bar 1, x1 bar. And I imagine all the things that could have happened for that sample mean, it will be a normal distribution as well. It will have still have a mean of 150, but its standard deviation will be smaller. And its standard deviation will be 50 divided by square root 25. And 25 is a helpfully square number, so this will be 10. And it'll happen over here too. So x2 bar will be from a normal distribution with mean 130 and standard deviation 10 as well. All right, and now what I'm actually doing is I'm combining both of these together to get one more new calculation, x1 minus x2. And okay, and x1 minus x2 is, I imagine all of this happening and all the things that x1 minus x2 could possibly produce, and that produces a normal distribution as well. And the mean of this normal distribution is this mean minus this mean, which is 20. And the standard deviation will be this squared plus this squared square rooted. Because that's how you combine standard deviations using Pythagoras' theorem. Like that. Cool. That's that. How are we going? Yep. And so if I was going to do actual working in paper, which you don't have to do, but I would say x1 is one individual from population 1, and so x1 is from a normal distribution with mean 150 and standard deviation 10, and x2 is one individual from population 2, and x2 is a normal distribution with mean 130 and standard deviation also 10, was it? Oh crap, this is 50. Of course, that would be too easy. That would be too easy. And so x1 bar is the mean from 25 people from population 1. They're not necessarily people. And x1 bar will be a normal distribution still with mean 150, but now the standard deviation, I can't be bothered. Mean is 150, standard deviation is the old standard deviation divided by the square root of the sample size, which was 25, which is now 10. And x2 bar is the mean from 25 from population 2. So x2 bar will be a normal distribution with mean 130 and standard deviation, the old standard deviation divided by the square root of the sample size, which is 9. And then x1 bar minus x2 bar will be a normal distribution with mean this minus that, which is 20. And the standard deviation will be the square root of 10 squared plus 9 squared, which is whatever the hell it is. Whatever that is. Not pretty. 14 and a bit. No. 13 and a bit. Okay, nearly 14. Because 196 would be 14, because I know my squares. Up to 15. No, 16. Yeah. Sorry. If I concentrate. Okay. So I want the probability that the sample mean from group 1 is greater than the sample mean from group 2. which is the same as the probability that x1 bar minus x2 bar is greater than 0. And this is a normal distribution with mean 20 and standard deviation root 181. So I can convert this to a z now. So here's my picture. Here's my picture just while I'm thinking of it. This is the answer for x1 bar minus x2 bar. The mean is 0. The standard deviation, no, the mean is 20. Standard deviation is root 181. And there's 0 there. And I want this probability here. And so that will be the probability that z is greater than, all right, so I take off the mean and I divide by the standard deviation, whatever that is. So that'll be the probability that z is greater than minus 20 divided by the square root of 181 minus 1.4866. You only got two decimal places in the z table? I think it is 1.49, let's say. And so that's the same as the probability that z is less than 1.49, because I had this side and I flipped it over to this side, and I can look that up in the table.
How are we supposed to do that in like 3.5? Is it, what is that, 3.5? 2 hours? What's it?
But for one question.
How many minutes is it per question? 50 questions, 2 hours?
Sorry? How many questions have you got?
50 questions in 2 hours.
2 hours. If it's 2 hours, like 120 minutes, and you got 50 questions, that's 2.5 minutes per question. But wait, you don't have to write all this stuff down. No, I can't either. But I can skip writing all of this words bit. I can skip writing all the words down. Yeah. I can skip writing the words down and go, okay, cool. And I know that this is going to be on root n, so I can probably skip straight to here. And say, well, the mean, yeah, but I probably would have to do it one step at a time. I could go straight to here. I could go, x1 bar will be the same mean and the standard deviation divided by root thing. And then I at least have this. And then this one will be whatever it is. And then this, yes, that would take a good minute and a half, maybe. Do not envy you. Which is why you want to go backwards. Anyway.
You know how you were converting the standard deviation through?
Yep.
I don't really remember that.
Your lecturer probably just straight up gave you a formula for what this is going to work out to be.
Okay.
So he's probably expecting you to go, oh, look, it's just this thing. And this one came from a Z distribution. He's expecting you to look at this, go, oh, well, if I go x1 minus x2 bar minus mu1 minus mu2 over this, and it's supposed to be a normal distribution, he was expecting you to go straight to there. I have trouble doing that. So that's the short version. The short version is, oh, I've got two populations, and I'm comparing the sample means, right? So I've got two populations. If I do this calculation, then this will be from a normal distribution with mean 0 and standard deviation 1, right? And so you're going to say the probability that x1 bar is greater than x2 bar would be the same as this being greater than 0. which is the same as this Z being greater than 0, right? Which is the same as the probability that Z is greater than whatever this works out to be. That's what he wanted you to do, probably. I wouldn't have thought of that.
So I could just use that.
Because this is exactly what I did. This is the x1 minus x2 bar, which I didn't need. And it was this formula here, right? That formula there is what went in this spot here. So I've got the mu1 minus mu2, which was the 20, minus 20 here. And this is the square root of 1 squared divided by, this works out to the same answer as what I had before. This works out to the 181. So that's what he was expecting you to do. Was that in the practice exam?
Yeah.
Okay. I wouldn't have thought of either. Under stress, I probably wouldn't have thought of either. But that's.
That would be one of the more, that would be like your HD.
Yeah. Probably. You're joining a lot of bits of information together to do that question. I'm going to stop the recording.